Hi everyone, welcome back to my channel. In today's video, I want to discuss the various things that affect the boiling point of a particular solution. Now this is a bit of a follow-on from last week's video where I discussed the various types of intermolecular forces and how that inevitably increases boiling point. Now in that video, I said one of the biggest things that affects boiling point is the strength of the intermolecular force. With stronger intermolecular attraction between different molecules, we see that boiling point and the vapor pressure increases. Additionally, molecular weight is also seen as a predictor of the boiling point of a solution. Take methanol and ethanol, for example. We know that ethanol has a higher boiling point than methanol, and this is because of that extra carbon and hydrogen atoms present in that particular compound. Now, the last thing that affects the boiling point is the number of branches that are present in a chain. So imagine you had a 5-carbon chain, and another compound also has 5 carbons, but it has many branches. Typically, we'd see that the 5-carbon straight chain will have a higher boiling point than one that has branches. So in today's video, I'll just be discussing each of these points in a bit more detail and how they affect the boiling point of a particular solution. But before I get into that, I actually want to talk about how boiling occurs. So imagine you had a cup, and that cup was filled with water. So for boiling to occur, the vapor pressure of that solution, or the water in this case, has to overcome atmospheric pressure. So a good way to think about this is that the atmospheric pressure is a force that prevents the liquid from becoming a gas, and the vapor pressure is what combats or it sort of counteracts this atmospheric pressure. So put simply, boiling occurs when the vapor pressure is equal to or more than the atmospheric pressure. So one of the biggest things that affects the boiling point is the strength of the intermolecular attraction present in that solution. So the 4 different types of intermolecular forces is the ion to ion, ion to dipole, dipole to dipole, or London dispersion forces. Now I covered these in my previous video, so if you don't know what these are, just go check that video out. But essentially, just for an example, water, we know has a boiling point of about 100 degrees, and this is because it has a particularly strong dipole to dipole force. In water, because of the electronegative charge or the electronegativity of the oxygen, we see that when water is in solution, this electronegative oxygen is attracted to the electropositive hydrogen. And because of this creates an attractive force between molecules, and this essentially prevents them from going from that liquid phase to a gas phase. And consequently, we see an increase in the boiling point. So for a given functional group, the molecular weight of a particular chain also increases the boiling point. As the chain increases in length and size, we see that boiling point typically increases. And this is because for a particular functional group, with extra carbons and extra hydrogens, we see that there's an increase in the London dispersion forces present in that particular compound. Again, if you're not sure what London dispersion forces are, please check out one of my previous videos. But essentially what happens with an increase in the molecular weight and an increase in the presence of these different atoms, we get a greater opportunity for London dispersion forces to occur. And this causes a greater attraction between adjacent molecules, therefore increasing vapor pressure and inevitably the boiling point of that particular solution. So one of the last things that affects the boiling point of a particular solution is how many branches are present in that particular compound. So just to go through an example, if we take pentane, 1, 2, 3, 4, 5, and we compare it to isopentane, so it looks like that, 1, 2, 3, 4, 5. We see that the boiling point of isopentane is 27.8 degrees Celsius, but the boiling point of pentane itself is 36.1 degrees Celsius. So the reason why we see this difference in the boiling point between these two is because in isopentane we have this one branch here. And this inevitably changes the surface area of that particular compound. So if we have a straight chain, we have a greater surface area, and with more and more branching, we get a decrease in the surface area. Now the strength of the intermolecular forces, or the van der Waals forces, is proportionate to the surface area of that compound. So as we increase the surface area, we increase the intermolecular forces. And as we increase the intermolecular forces, we increase the vapor pressure and thereby increase the boiling point of that particular solution. So that's everything for this video. I hope it was useful in some way and just helps to clarify some of the things that alter the boiling point of a particular solution. If you found this video useful, please drop a like below, and I'll see you guys in the next video.